Hello class, how are you doing? This is, what is it? This should be your second lecture that you're doing in week 7. Now there's been a little bit of an update. If you haven't done this already, if you haven't got that email from registry, this is now only a 9-week teaching semester, not 10 weeks. It started off as 14 weeks, got reduced to 13, then 10, and now we're down to 9. So we're chasing a shifting goalpost here, guys. I'm very sorry about that. We're just going to have to be quite flexible because of the coronavirus. But anyway, you should have finished masonry. There were 2 lectures on masonry, and assignment 5, which is about masonry. That is due on Sunday, the first day of week 8 at midday. But the new type of material we're going to be looking at is wood and wood products. So in this section, you're going to be learning about different kinds of wood and also products that we can make out of wood, which we basically alter and change into a different kind of building material. We call those wood products. We're going to be looking at some of the key properties of different woods and how they vary. We're going to also talk about how you treat wood. You can't just cut down a tree, get the timber out of a tree, and then use it in a house. That's going to rot very quickly. There's treatment for woods in order for it to have good property. We're also going to be talking about the availability and compatibility of wood in various civil engineering applications, much like we've done with other materials thus far. And we're also going to be talking about the manufacture of key wood products, so things like chipboard and plywood. These are wood products that are very common in Kurdistan. And we're going to be talking about these materials in relation to Kurdistan. So I just want to give you a couple of definitions. From now on, we're probably not going to talk about wood, just so you know. Wood is really sort of a scientific term for the material, but in terms of engineering, we use different terms depending on the process of where the wood is sitting in its development. So initially, wood is cut down from trees, and those logs you see there, we would call that lumber. So it's untreated wood that's just been cut down and felled. And then when it is milled into various shapes which are useful, we would call that lumber would become timber. Timber is lumber that has been milled into various shapes, planks and bars and poles and that sort of thing. And there's another type of product that you can make out of lumber, and that's a variety of wood products. So that's a picture of chipboard there, where basically lots of small chips of wood or lumber are stuck together and compressed in a resin. So that's a chipboard. You've probably seen that around. There's a few other wood products we're going to look at. But remember those terms, especially lumber and timber. Those are the terms we use a lot more than wood. So what kinds of wood are there? So wood is the term we use before the tree has been cut down, really. Well, there's 2 kinds of trees, effectively. You have what's called an evergreen tree, and an evergreen tree is effectively what it is, what it says it is. The tree is always green. It does not lose its leaves in the winter. And then you actually have another kind of tree, which you're probably not familiar with this term, deciduous. That's the kind of tree that actually has flowers in the spring, and in the autumn, the kharif, all of the leaves fall down and the tree basically, it looks like it's died. It almost hibernates. And yeah, that's called a deciduous tree. So here in Kurdistan, I think most of your trees that grow in the wild, in most of your forests, I think the bulk of them are deciduous trees. But you do have a few evergreen trees as well. In New Zealand, we have no deciduous trees. All of our trees are evergreen. That's because New Zealand doesn't, in most parts of New Zealand, there aren't really any seasons. The weather is sort of temperate year round. In places where you have a very definite summer and winter, you tend to have more deciduous trees. Now, the types of wood that you get from these two trees are slightly different. An evergreen tree, the wood you get from an evergreen tree, the lumber, once you mill it, once you cut it down, that's something that we call softwood. And a deciduous tree, when you cut the lumber out of a deciduous tree, that's called hardwood. Now, this is rather confusing, I know, but a softwood is not necessarily a wood that is soft, and a hardwood is not necessarily a wood that is hard. You can have you can get some woods that are very soft from deciduous trees, and you can get some woods that are very hard from evergreen trees. But these are just terms we use, softwood and hardwood. Very confusing. It makes no sense to me. I'm not sure how the English language evolved into that direction. I really don't know. But I'm labouring this just so that you understand. What you need to remember is if I say softwood in one word, if it's written in an exam question and I write softwood in one word, like you see there, that I'm meaning a wood that has come from an evergreen tree. I do not mean a wood that is soft. If I was meaning a wood that is soft, there would be a gap between the two words when I say softwood. It would be two words. One word soft, one word wood. Does that make sense? Yeah, confused yet? Yeah, well, welcome to civil engineering. Now, there is something that you do need to know. The difference between softwoods and hardwoods is it's not actually their hardness. But remember, a deciduous tree, basically all the leaves fall off for about half the year. Now, leaves are actually what collect sunlight and start the process of photosynthesis. That is what actually makes the tree grow. So basically, a deciduous tree is only growing for usually 6 to 9 months of the year. An evergreen tree, on the other hand, is growing for 12 months of the year. What does that mean? Well, generally, and this is a generalization because there are some very slow-growing evergreen trees out there, generally, evergreen trees grow faster than deciduous trees. And because they grow faster, generally, softwood is cheaper than hardwood. Because if it only takes 30 years for the tree to grow, then it's going to be cheaper than lumber from a deciduous tree that took 50 years to grow. Do you understand that? Because increasingly people are not cutting down forests from the wild. They're planting forests with the purpose of trying to harvest the lumber in 20, 30, 40, 50 years' time, depending on what kind of wood they're trying to produce. Now, something like radiata pine, which is a type of evergreen tree, that could take anywhere between 15 to 25 years to grow to a point of harvest, whereas a deciduous oak tree, that might take 50 years to grow. Now, just to give you an idea, just as a good example, an evergreen tree, it's a generalization that they grow faster than deciduous trees. That tree you see there, that's actually a New Zealand karri tree. This is actually a tree not far from my home, actually. I live quite close to this forest with these giant trees called karri trees. Now, that tree there, that's actually my sister, by the way, Janine. That tree there, it's got a diameter of 6 meters. It's I think it's one of the largest. It's in the top 10 trees in the world for size. But that tree there is about 2,000 years old. It grows very, very slowly. So this was a little seedling at the time of Jesus Christ, and by the time of Muhammad, this tree was already 700 years old. So that gives you an idea of the age of the tree, and the fact that actually some evergreen trees do grow very slowly. And this is actually a karri tree. That's in New Zealand, the karri trees are protected. You're not allowed to cut down a karri tree, but this was a karri tree that fell down in a storm, and they said, well, we shouldn't let it go to waste, so a company decided to go in and mill it with government permission. And so, yeah, you can see how much karri is in there, how much wood is available just in that one stump, and I actually know what happened to this wood. It actually built an entire house. So the wood from that one stump was enough to build a house. And that's the largest tree in the world. That's also a New Zealand karri tree. The people are standing a little bit further off there. But yeah, that has about a 6 to 7 meter diameter at the base of that tree. So how do we know how old these trees are? Well, there's actually, the only way to know for sure is actually to cut down the tree. Now, if you cut down a tree, you're actually going to see lots of rings inside the tree, aren't you? Well, what does that mean? Well, first off, on the outside of the tree, you're going to have something that's called bark. This is basically like a protective skin for the tree. And it's also where insects live. It protects it's basically the tree's natural paint. It stops the wood on the inside from rotting. And so when we mill lumber, we actually cut away the bark because it's actually quite weak and flaky, and then that bark we use that's waste. We might use it for something, but usually it's waste. But inside the bark, you have all of these little rings. Now, the number of rings determines how old the tree is. Basically, trees will grow faster when there's a lot of sunlight and rain, so they grow faster in the spring and summer. And then in the winter, especially if it's a deciduous tree, because it loses all of its leaves and stops growing entirely, it slows down how it's growing. Now, when it's growing quickly, you basically get fast growth, and that is shown by the light rings inside the bark, inside the lumber. But when it's growing slowly in the winter, it slows down, and those rings are how much it expands in the winter, those dark rings. And you can see the dark rings are quite a lot narrower than the white rings. So what does this tell us? Well, by counting all of the dark rings, we can actually work out how old the tree is. So if you actually want to pause this video and count all of the rings there, you can work out how old this tree is. I don't know, I'm guessing it's around 30 years old or so. Now, you will also notice that there are the rings on the outside. There's a tendency for them to actually be closer together than the rings on the inside. Now that actually creates two different kinds of wood. The outer part of the wood, of the lumber, that's what we call sapwood. Now sapwood generally is less durable and softer than the middle wood, which is called heartwood, and it's also less strong, the sapwood. Heartwood, that is the strongest and hardest timber that you can get from the lumber. So even within the tree itself, you actually have a variation in property for the wood. So that's a very important thing to remember. Now, one of the things with sapwood is that it's softer and it's easier to penetrate with liquid. Now because it can be penetrated with liquid, it actually means it can get damp and moisture can get in, and then the moisture can get out. We'll talk about that later, but it makes it less durable. Basically, it can rot a lot more at a faster rate than, say, heartwood. But the other benefit, but there is an advantage. If it can be penetrated with a liquid, you can penetrate it with a chemical, and this is called chemical treatment. We'll look at this later, but chemical treatment can stop a lumber or a timber from rotting. We'll talk more about that later. And the very middle point of the lumber, where all of those rings converge, that's called the pith. I don't know why you need to know that, but I kind of think it's a bit of a funny word, pith. So I'm just going to pith off to the next slide now. Now, if you actually were going to look at wood under a microscope, it's actually quite incredible. Basically, all of the cells inside wood are basically long, singular fibers, and they all align with one another almost in a grid pattern. It's almost like masonry, isn't it? And on the outer side of each cell wall, there's this real sticky frictional resin that we call lignin. Now basically it's very, very hard to pull these cells apart, and that's why wood can have some excellent tensile strength. If I had a piece of wood and I was pulling it apart, one end I'm pulling and the other end I'm pulling, and I'm pulling parallel with how these cells are aligned, it's going to take a lot of load before the wood will break. Timber has really good tensile strength, so long as the tensile loading is parallel with how these cells are arranged. That's a very important thing. So you have a big tall tree going from down to up. These cells are arranged down to up. If you're pulling in a different direction, then it's going to have very weak tensile strength. But I can tell you that I believe in creation. I don't believe in evolution. I believe trees were well designed by a very powerful and almighty God. I just cannot believe that something like that came out by accident. When we are trying to develop materials as engineers, we can't develop anything as efficient as wood. It's just quite incredible, just the strength that comes from wood. So I'm now that we've covered a little bit of what is wood, we've looked at some of the terminology, we've looked at what are the different parts of trees, what are the different kinds of trees. Let's now look at different properties, and then after we've looked at the properties, we're going to talk about applications to civil engineering, I hope. So the first property we're looking at is moisture content. So moisture content, well, we've done this a little bit already now, haven't we? We've looked at moisture content with aggregates. We looked at moisture content with masonry, and it's basically a measure of porosity, isn't it? Well, this is very easy. You basically need to take a piece of wood, soak it in water, weigh it, and then dry it in an oven, and the difference is the mass of water, and then you divide that by the oven dry weight of the wood sample and you multiply that by 100. That gives you the moisture content of the wood. Now, very simple calculation. You do this for masonry, you do this for aggregates, you can do this with a number of different woods. But where is the moisture being held? Well, it's actually being held inside the cell walls. So when you have, remember how I showed you the wood cells, how they were these long fibers? Basically, the moisture gets between these fibers. So what's that going to do? Well, it's actually going to reduce the friction between the fibers. And so generally, the higher the moisture content in a wood, the lower the strength. And it also affects durability too. We'll get to that later. But durability, basically bugs and bacteria and fungi, they can break down and eat the wood if there's moisture there. But the moisture content, that reduces the strength and it reduces the variability. The durability, sorry. Now the moisture content, that's going to vary depending on what type of wood. Generally, there's more moisture content in evergreen or softwoods than there is in deciduous trees or hardwoods. That's a generalization. But what is not a generalization is that the moisture content, or the height of moisture content that can be raised to, is higher in sapwood, that outer ring of the lumber, than heartwood, the inner rings of the heartwood. But anyway, trees, when they are alive, they're just like human beings. I think human beings, we are around 75% water or something. Trees are the same. They have water inside them. It's part of being a living thing. So when you cut down lumber from a tree and you mill it and you make timber, before you can use that timber, you need to dry it. You need to get the excess moisture out of the tree, because that's going to give the timber more strength and more durability. So what does drying look like? Well, once the timber is milled, that means it's cut into the various shapes. It needs to be dried out for a period of time. Now, you can't just cut the timber, cut down the trees, mill it, and then immediately build a house out of it. You're going to have all sorts of weaknesses and rot and flecks, all sorts of problems. So remember, the moisture content is generally higher for sapwood than it is for hardwood, and generally higher for softwood than it is for hardwood. Not woods that are soft and woods that are hard, but softwood and hardwood. Now, when you're drying it, the moisture content will drop. Now, you cannot drop the moisture content of the wood down to 0%. That's absolutely impossible. You can reduce the moisture content down to something which is called equilibrium moisture content, EMC. Well, what's that? Why can't you go to 0? Usually it'll be around 5-10% or so, the EMC. Well, that's because there's water in the atmosphere, isn't there? It's what we call humidity, or rutuba in Arabic. And so as long as there is humidity in the atmosphere, there will always be some moisture inside the timber. And you need to reduce it to the minimum, which is called the equilibrium moisture content. And that is dependent on the humidity, the environment, the weather that the timber is being used in. So that's what drying looks like. So just so you see here, that picture on the right, that's a drying shed. My best friend growing up, he actually lived on a farm, and they had a forest on the farm, and so from time to time they would cut down trees and mill the timber from the trees, and they would stack the wood in this drying shed. And so you can see in there that there's actually, where the timber is laid, there's little spaces in between all of the timbers. Do you see that? That's so air can get in between all the different slots and dry out the timber individually. How long do you think we have to dry the timber before we can use it? Well, that's going to depend on the type of wood. It's going to depend if it's what the moisture content is when we first get it, and so forth. It also depends on how we dry it, but in just an open drying shed like that, I can tell you that we actually waited 2.5 years. You cut the wood, you cut the trees down, you mill the lumber into timber, you stack the timber in the drying shed, and then in this case we waited 2.5 years before the wood dried out and it hardened and it became strong, and then we can use it. So this is something that a lot of people, particularly in the Middle East where you don't have a lot of wood, they don't actually realize that. You can't just use wood straight from a tree. You've got to dry it out, and that drying process can take a long time. So when we are drying something, when we're drying the wood, the timber, what we do, this is actually called seasoning, if you like. Now, one of the ways we can dry wood faster is actually to have drying sheds which are enclosed and heated. And so this is actually what's called kiln drying. So remember we talked about that word kiln when we covered masonry. Kiln is not an oven. It is an oven. That's what it is. But an oven in English is something that we cook food in. A kiln is something where we prepare materials for building. Now, these kilns will actually raise the temperature, and because the temperature is higher, they will actually dry out the wood faster. So rather than having to leave the timber in a shed, an open shed, for 2.5 years, you can put it in a kiln drying station like this, and the wood will be ready within a few days. So that's a great way to, if you need to reduce the amount of time and you need to use the wood quickly, then this is a way that you can do it. Of course, there's a lot of expense when you're basically drying out the wood with a kiln. You can't. There's not a lot of expense involved in just leaving it in an open shed. Now, you can't just crack up the heat. You can't just turn it up to 200 degrees Celsius and think, "Oh, I'm going to dry it really quickly." Well, first off, if you put the temperature up that high, what's going to happen is you're actually going to get the wood catching fire, and you're going to create a big fire. You don't want that. But the other thing is, even if you don't reach the point of combustion and it doesn't catch fire, if you dry it too quickly, basically the timber will crack. That means as water is sucked out of the timber between those cell walls, those wood fibers inside the wood, those cell walls, they will not stick to one another with the lignin, that natural resin that they emit. Instead, they will split apart, and you will end up with big splits in the wood, and that loses all of the strength in the timber. The other thing you need to remember with kiln drying is you've got to have extractor fans to get the humidity out of the timber, because if you have a big closed shed like that and you're heating the wood inside, while you're heating it, all of the moisture is going to come out of the wood, but then it's going to be stuck in the shed. You need extractor fans to pull out the moisture, and you can probably just see that in that picture. If you look above the timber, you can probably see 3 really big extractor fans, and they're drawing the humidity out of the oven. So that's kiln drying. Now, normally with kiln drying for timber, normally you would raise the temperature to, I would say, about 40 to 50 degrees Celsius. That's probably as hot as it goes. Usually it's about 40 degrees, I would say. So it's not really that much hotter than Kurdistan on a hot summer's day. And by doing that, they're making sure that the wood doesn't dry too quickly, and they're increasing the strength of the timber and the durability at a faster rate than if they had left it in an open drying shed. So these don't have a lot. I don't think there is any kiln drying happening in Kurdistan, because you have these lovely hot summers, which reduces your need for kiln drying. But in a lot of places in the world, where they grow lumber, because they can grow lumber there's a lot of rainfall and there's a lot of humidity. Therefore, they will often have kiln drying. Now, what happens with moisture content and its effect on durability? Well, remember what I said, that moisture inside timber sits between those fibers, those wood cells, and it actually expands the wood, because it actually means the wood cells are sitting a little bit further apart, because the water dilutes the resin, the lignin, that sticks the wood cells together. Now, what you need to know here is that moisture content in and of its own does not lead to low durability. No, what leads to low durability is not high moisture content, but variation in moisture content. So basically, that water that is sitting in a high moisture content wood between the cell walls, when that dries out and the wood goes to low moisture content, those cell walls, those 2 wood cells that are sitting next to one another, they're going to basically split as they're dried out. And then when you get more rainfall, more wood will go into that cavity, and then it will dry out, and the wood is constantly swelling and shrinking. So look at that picture of the wood there. Is that a good piece of quality wood? No, it isn't. That's actually quite old. We would say that's old wood, and it's got all of these cracks inside it. What's caused that cracking? Well, it's the swelling and shrinking of the wood going from high moisture content to low moisture content. What's causing that variation? Well, it's the weather. If you have a very rainy day and then a very dry day, a very rainy day, a very dry day, you're going to get variation in the moisture content, and that's going to lead to this swelling and shrinking. And so that's why it's very important to have treated timber that can stop this, or have if wood is exposed to the environment where it's always wet and then dry and wet and then dry, you paint it so moisture cannot actually get into the wood. You give it a waterproof barrier by painting it. So this wood here was not painted, and you can see that there's been a lot of damage to it from the swelling and the shrinking. It causes splinters in line with the wood fibers. Do you also see how all of those splinters there inside the wood, those cracks, they all go in one direction, don't they? Because they're running parallel with the cell fibers, the cells, because effectively they're gaps between the cells, the wood cells, the fibers. And when you look at it through from one end of lumber, what you actually get is what's called radial splitting. So basically all of the wood fibers with lumber, when you're looking at lumber at the face, so you can see all the rings from the seasonal changes, and you can count the year and the age of the wood. Basically, the fibers right now, the wood fibers, are going into your computer screen or coming out of your computer screen. That's the direction they're heading. Now, when you have high moisture content, low moisture content, it's going to actually split those wood fibers. And so when you're looking at lumber from one end, basically the cracks that emerge, they are radial. They go from the outside to the middle, and they all conjoin at what is the pith. So when you have big cracks like that, you're drastically reducing the strength of the wood. Drastically. You're probably reducing the strength by 90+%. So yeah, remember that moisture content, it's variation of moisture content that leads to erosion and a lack of durability in the wood. It leads to the weathering of the wood. But moisture content, if it does have its advantages at times. If it actually has high moisture content, the wood can actually deform. That means the wood is softer. You have more room to it actually means the gaps between the wood fibers is larger, and so you can bend the wood into different shapes. Now this can be a problem if you don't want it to bend. If you want a nice hardwood with no elasticity in it, well, that's going to be a problem. But sometimes you want it. So you can see here a timber, it's flexing in different directions, and that's because of high moisture content. And the direction that it bends, that will depend on where the load is being applied. But that's being caused by a high moisture content. But we may want to be able to deform the wood, and we'll get to that later. Now, the other thing which really influences the porosity of the wood and the amount of moisture content a wood can hold is the density of the wood. Now, we tend to measure density, like many materials, we measure it by specific density or specific gravity. So it's basically a ratio of the wood's density to the density of water. Now, the way we measure wood density is a density is basically a mass over volume. But this is something quite important. The way we measure wood density is the mass. We take that from the oven dry weight of the wood. So we dry the wood out, we get it right down to what is the EMD, equilibrium moisture, EMC, equilibrium moisture content, and we divide it by the volume of the wood when it's green, meaning when it's first cut. So that's how we work out density. And this is just a way to have it standardized, because obviously the density of the wood is going to vary depending on what the moisture content is. Now, the density of the wood, we do this as a specific gravity, okay? So as a ratio of the density of water. Now, it's going to vary depending on the species of tree. It's also going to depend on whether it's heartwood or sapwood. Heartwood generally has a higher density than sapwood. Oak generally has a higher density than cedar. And you can see two examples there. The density of oak is 0.9 and the density of cedar is 0.3. This is something else which is a very good property of wood. It's very, very light. It has low density. Often the density of wood is lower than the density of water. In fact, that's actually very common. It's usually lower than wood. And that's one of the reasons why wood floats compared to most other materials. And that's why it makes a very good material for things like boat building, where generally the speed of the boat depends on how light the material is that it's made out of. So it's very light, but unlike other light materials, things like polystyrene, which has very low density, the big difference of wood is that it's very strong. Very strong. It's got very good tensile strength. And so this is one of the wonderful things about using natural materials as opposed to materials which are manufactured, things like carbon fiber and fiberglass, is you get to really appreciate the ability, the incredible power of God and His almighty creativity in creation, if you like, because these materials that He has created are far, far superior in properties than anything that we can as human beings produce. Concrete is very strong, but hey, the density of concrete leaves a lot to be desired. Wood is one of those materials that doesn't seem to have the same level of compromise. Now, there's a very good general rule, and it's pretty hard to find exceptions to this, but there are a few. Generally, the denser the material, the stronger the timber. And we're going to look at strength in different directions, compressive, tensile, flexural in a little moment, but generally, the denser the wood, the stronger the timber. Now, what is something else that can affect the strength of a timber? Well, it's something called defects. Now, a defect is basically any part of the timber where things have become irregular. So there's three different defects that I'm going to teach you here. The first one is, the first two are basically cracks that emerge in the wood, and these are basically usually caused by variation in moisture content from the wood getting wet and soaked and then dry again, wet and soaked and then dry again. That causes these cracks to emerge. And there's two kinds of cracks. One is called a cheek. Now, a cheek, that is a crack that emerges, or split, that runs perpendicular with the grain of the wood. If you look at the edge of the wood there, on the end of the timber, you can actually see the rings from the lumber, can't you? A cheek runs radially with the grain. It runs perpendicular to it. A shake, on the other hand, is actually where it actually splits with the grain. It sort of separates the wood rings from the lumber rings. And so usually a shake, there will actually be a little bit of curvature to it because it's following the curve of the ring of the lumber. Now, a knot is basically where a branch was coming out of the trunk of the tree, and so when you cut the trunk down and then you mill it, you have these little knots that emerge, which is where the branch of the tree was coming out. Now, what you need to know is that these defects, they can reduce the strength of the timber drastically, and I mean by up to 90%. It's a huge factor in lowering the strength of the timber, up to 90%, I would say. So this is very important because when you are building a house or building a wharf or walkway and you're using timber, you don't just ask for the timber and say, yeah, please deliver so much 6x2 timber and so much 4x4 or whatever. These are different sizes of timbers, by the way. What a good project manager would actually send an engineer who knows what he's doing, it's probably a UKH graduate, to the shop, and you select which timbers you want, and you select the timbers that don't have these defects, because those are going to be the timbers which have maximum strength. You don't let the guy in the wood shop, the lumber and timber shop, to select the wood that he's going to give you, because if you do that, he's going to give you the timbers which have the most defects, the knots, the cheeks, the shakes. They reduce the strength. So that's another very important thing to look for when buying timber. There are other properties of wood, and that is that they look different. One of the important things for a lot of people buying wood is the aesthetic quality. They want to see the wood, and they want to see what color the wood is, and how that actually influences the design and the architecture of the house or whatever it is you're building. So there's a lot of variation in color, I would say, with wood. So generally, woods such as oak are very light in color, and woods such as walnut or cherry or mahogany, they tend to be a lot darker in color. And so that's an important thing to remember too. These colors that you see here, these are not being influenced by the varnish. The varnish is basically see-through paint. The color is coming from the timber itself. So if you're building a timber floor, know that the type of timber you use, the type of wood, that's going to influence the color. And also you can see there's big variation in the grain. Some woods have very noticeable grains, things like pine. Others are much slower growing trees, things like teak or mahogany, and so the grain actually is a much swirlier pattern, and so that can give you a different give you a different look too. It's sort of it's got this sort of marbly look to it, which I think is very attractive. Now we're going to go on to another property here of wood, and we're going to look at the modulus of elasticity. So we did modulus of elasticity with other materials. We looked at it with concrete, we looked at it with aggregate as well. Now we're going to look at the same property with wood. Now remember, with modulus of elasticity, there's actually two kinds of deformation. There's elastic deformation and there's plastic deformation. So elastic deformation is basically how much the wood stretches or is compressed, depending on whether it's compressive or tension load, that it moves, and then when you take the load off, it bounces back to its original shape. You're trying to work out how much elasticity there is, just like an elastic band. And then there's plastic deformation, where basically the shape of the wood changes permanently. You can reduce the load, take the load off, but the wood has permanently changed its shape. It's been deformed. But that can happen before failure, before the wood actually breaks. So remember, with concrete and aggregate, there was very little plastic deformation. Basically, once it started moving permanently and there was plastic deformation, a nanosecond later of increased load, the concrete broke. With wood, there is actually more plastic deformation. Now, the modulus of elasticity can vary a lot between species, but again, a general rule is softwoods have more elastic deformation than hardwoods. That's elastic deformation in both compressive and tensile loads in both. And what you need to remember too is that the plastic deformation, not elastic deformation, that increases with moisture content. If the wood has a high moisture content, it's going to have a lot of plastic deformation potential. And that's a problem, but it can also be a very useful property, because it means you can shape the wood in all sorts of curvature. We'll get to that later. So let's look at the modulus of elasticity here. One thing, we're looking at the modulus of elasticity in compression here, and you can see that there's actually a bit of a variation here, but the modulus of elasticity, it's going to be a little bit different depending on whether it is the compression is happening parallel to the grain or perpendicular to the grain. If it is parallel to the grain, it's going to be stronger, but also slightly more elastic. And what we're looking at here is all of these woods, they have a moisture content of 12%. So we're comparing apples with apples here. And you can see immediately there's quite a variation in elasticity. You've got 4 to 10 megapascals for cedar, 8 to 15 megapascals for oak. But first thing you should notice is that the modulus of elasticity is quite high for wood compared with concrete or aggregates. Remember, the modulus of elasticity for those, we were measuring it in sort of 35-40 gigapascals, and so it was a lot less stretchy or squishy compared to wood, which is what you would expect. But you've got to remember that as an engineer, as a designer, that there will be more flex in the wood, and so you need to remember that if you're building a house or a high-rise out of wood, there's going to be more flex. Now, what you can see there that I've actually listed 7 different kinds of trees, and they've all got different moduluses of elasticity, but you'll see that 4 of them are in black and 3 of them are in red. What is the distinction I'm making there? Well, for those of you who might be paying attention, the ones that are black, that's evergreen trees. Those are softwoods. And the red ones, those are deciduous trees. Those are hardwoods. So what you should be seeing there is that actually, generally, there's marginally more elasticity, and that is shown by a smaller number, because remember Young's modulus of elasticity, the smaller the number, the more elastic it is, with the softwoods than there is with the hardwoods. So that's modulus of elasticity there in compression parallel to the grain. But sometimes we want to have flex in the wood. First off, it's very useful for absorbing shock loads, things like earthquake, horizontal loads. That's one of the reasons why in New Zealand most of our houses are built from wood. First off, we have a lot of wood in New Zealand, but the other advantage of it is that we actually have problems with earthquakes, and so wood is a lot safer than masonry blocks in an earthquake. But I now want to talk to you about one of the advantages besides earthquake loads that wood gives us in terms of malleability. When a wood has a high plastic deformation, because it has a high moisture content, that means we can actually bend the wood into new shapes. One of the difficult things with wood is we can be quite restricted in the shapes we can use. With concrete, we can make a mold in any shape we want and make a concrete block in that shape. We can make statues out of concrete, no problem. But wood, it takes a little bit of work trying to make it into different shapes. But if we want wood to be bent into a new shape, what we can do is we can increase the moisture content of that wood. And we can do that by soaking it in water, or more likely we put it under high pressured steam, and that the steam can actually get into the wood faster than if you just soak it. And then once it's got a high moisture content, you can bend it into a new shape. And then what you would do, when it's in the new shape, you would dry it. And you need to be careful. You can't dry it too quickly, otherwise it will split. You need to have temperature control and everything to reduce the humidity over time, just like we talked about with the kiln dryers. Once it's dried, it's going to stay in its new shape. It's not going to bounce back into its original shape, because basically you've bent it under plastic deformation. So what sort of woods would you use this, would you need to be able to do this? Well, it needs to be a wood that has the potential to have a very high moisture content. And I mean a moisture content that could be up to 200% or even higher. So literally 2/3 of the weight of the wood is actually water inside it. And if it can hold a very high moisture content, you can bend it into a new shape. So a good material would be something like oak or mahogany or karri. Those woods, they have the potential to hold a very high moisture content. Karri, for example, that can actually hold a moisture content as high as 400%. And so when it's got a very high moisture content like that, you're thinking, well, that's terrible, that's low durability, that's low strength. Well, yeah, it is, but it does mean you can bend it into new shapes. And then when you dry it, you're going to have it very strong and very durable. What does not work so well are woods such as pine, bamboo, and fir, because basically they do not have the ability to hold a very high moisture content. Think of bamboo, for example. That's got a very waxy texture to it. If you were to soak that in water, and then dry it out, it's going to split very easily. And the amount of water that can be held inside bamboo is quite small. I think the moisture content for bamboo never goes higher than about 40-50%. And so bamboo is not a wood that you can actually bend into a new shape. Basically, the shape the bamboo comes in, that's the shape it's got to remain. Pine and fir, they don't have particularly good malleability either. They're fairly stiff woods. But this is what we can do with malleability. We can bend wood into all sorts of wonderful shapes. So it's a very important thing in boat building, because it's very important that boats don't have just angular curves. They need to be very curvy, the hull of the boat. But that's a bench there. This I thought was very beautiful. This is actually an old antique, it's an antique rocking chair that's made from wood which is teak, and yeah, this is about 80-90 years old. This was owned by a friend who lived in Oman, and I said, that's a really beautiful chair, can I take a photo of it? So that's a very old chair. That was done back in the about 80-90 years ago, I would say the age of that chair is. So this idea of steaming wood to bend it into a new shape under high moisture content and then drying it out, that's nothing new. That's been happening now for a good 200-300 years, since the Industrial Revolution, effectively. This is actually a piece of artwork. No, it's not a piece of artwork. I was visiting an art gallery in Germany, and the art, I don't know what it is with art. I don't really get it. I think most of the modern art people are doing today is absolute rubbish. I don't understand art at all. But in the art gallery, they actually had this bench where you could sit down and look at the artwork, but I just thought the bench was the coolest thing, so I took a photo of that. So that bench, that's actually made from timber, and you can see it's timber that's been made into lots of very thin strands, and basically it's been heated under hot steam, and the moisture content has been raised, and it's been bent into all of these wonderful shapes, and then it's been dried, and so to give it its good strength and stiffness. So another good example of malleability there. And but yeah, the one example that I think is best is in boat building. Yeah, wood is a fantastic material for boat building because, as I said, it's very strong, but at the same time it's very light. It's got low density, so it's good for boat building. Now, one of the important things with boat building too is that you need to be able to get the material, whatever you're building the boat out of, into a nice streamlined shape. into a nice curve. And wood, you can do that. So the wood that was used to build this boat for the hull, you can see the hull, it's a nice curve. They would have steamed it with hot steam to raise the moisture content, and then they would have bent it into shape, and then they would have slowly dried it, and that way it would have increased the strength of the wood. So that's malleability. Oh, and going back to civil engineering, we're building civil infrastructure, so things like houses and hallways. Isn't that beautiful? I mean, I have to say that wood is one of the most attractive materials, potentially, that you can use in civil engineering. But you can see that house there, that's got a beautiful dome roof to it, and you can see all of the struts going up to that point. They've been bent and curved into a shape, which creates this dome. Isn't that beautiful? Wouldn't it be great if some of the mosques had domes that looked like that? It would be a lot more attractive, I think, than often the concrete domes that they're usually building. Well, I think that's probably enough for this lecture. I'm seeing that I've gone over 1 hour, and I want to try and keep these lectures under 1 hour. I tend to lecture a bit quicker with these videos than if we were in a classroom, so I don't want to overwhelm you. If you want to do some supplementary reading on wood, then go to these pages in the Somayachi textbook. As I said before, this is supplementary reading. There is nothing that I will test you on that hasn't been covered in the lectures, but some people just prefer learning through reading. So see if you can get your hands on a Somayachi textbook, and I can there is one in the library right now, and I believe I don't think you are allowed to go on campus. That won't work. It's supplementary. Ask your colleague who has one. I think 3 or 4 of you have the book if you want to borrow it. So we've covered today, just as a quick recap, we've covered some terminology, some new vocabulary for wood. We've talked also about the importance of moisture content and how we can decrease the moisture content. We've talked about how that improves strength and durability. We've talked about how wood can decay because of variation in moisture content. And we've also talked about the advantage of moisture content when we put it really high. We actually can increase the elasticity of a wood. That means we can actually bend it into a new shape, and then when it dries out, that reduces the elasticity, so basically the wood stays in its new shape. Next week we're going to talk about strength of wood, and we're also going to talk a little bit more about durability. So thank you guys, and God bless.